Alright you guys, so our last kind of problem for this video set deals with finding specific solutions for kinematics-based problems. So here, in the past, we've gone from position to velocity then to acceleration. So we're just working backwards with the integration process to go from acceleration to velocity, and then from velocity to position. So you have this example problem here, and it tells you that your initial height for the structure that you're given is 56 meters tall, and then that we're launching up in the air at a rate of 2 meters per second. So those are some of your initial conditions that you're then going to use to come up with specific conditions throughout the problem. So, giving ourselves a little bit more room to work on this slide here, the first thing that we are asked to identify is the velocity function. So the good news is that if we're launching things up into the air on Earth, we know that our acceleration that we're working with is negative 9.8 meters per second squared. So if we want to go backwards from acceleration to velocity, all that we're doing is taking the derivative of that value with respect to time. So when we do that, what we end up with here is going to be that our velocity value becomes 9.8 times time plus a constant value. So if we have our acceleration, then this is going to become our velocity value. But what we can do then is consider that we know what speed we had when we started out. So you can think of that as your input x is 0 and your output y would be 2. So we can use that as an initial condition here. So we can say that 2 is equal to 9.8 times 0 plus our constant. So our constant must be equal to 2. So that allows us to be a little bit more specific than just saying add a constant at the end. So our velocity position here, or our velocity function here is going to be 9.8t plus 2. So that's our full specific solution to part A. Then part B asks you to identify the position function. So that just means we need to go backwards once from velocity. So we can go ahead and take the integral of this expression. So velocity is equal to 9.8t, so when we integrate velocity, 9.8t plus 2, with respect to time, we'll end up at that position function. So all we're going to do is increment up 1 from the exponent on our t, so you'll end up with 9.8t squared over 2, and then plus 2t plus a constant. Now, real quick, I lost my negative here when I got started, so I should have a negative here, a negative here. That doesn't change the constant because I was multiplying by 0 here. So a negative here and a negative here as well. So that means the general function for position is going to be negative 4.9t squared plus 2t plus a constant. But then we actually have information about the original position as well. That's just the starting height in this problem, which is going to be that 56 meters. So we can go ahead and substitute that in. So we can say for position, I'm going to come over here on the left, when time is 0, so when the 1 first launches, we've got times 0 squared plus 2 times 0 plus a constant is equal to 56. So this term goes away, this term goes away. Our constant here is just 56. So the specific position function is going to be negative 4.9t squared plus 2t plus 56. And notice that this should be a position function we're pretty familiar with. That's your negative 1/2 acceleration times time squared plus your velocity times time plus your initial height. So if you work backwards from acceleration, you get to that kinematics equation that you probably have seen a lot of in your physics classes. Then from there, you guys, we can use those functions to answer C and D. So C says, when does your wand reach the maximum height? That's just going to happen when your velocity function is equal to 0, because remember, derivative of position, set that equal to 0. You're just finding the first derivative test work there. So this is going to be negative 9.8t plus 2 is equal to 0. So negative 9.8t is equal to negative 2. We can divide over that negative 9.8. And so if you plug that in, 2 over 9.8, you're going to get t is equal to 0.204 seconds. So it reaches the maximum height pretty soon after it's launched into the air. Last thing is just asking you to identify when the wand reaches the ground. So all you're going to do for that is set your position function equal to 0. So if you do that, you've got negative 4.9 t squared plus 2t plus 56 is equal to 0. And you can just go ahead and graph that in your graphing calculator or use your solver. So if you want to get practice in with your solver, remember that you hit your math and then go down to the bottom. Then to modify your first equation, you just have negative 4.9x squared plus 2x plus 56. Hit your alpha button and enter, and then hit your alpha button and enter again. And when you do that, you would get a t value of 3.591 seconds for your final answer, so when it lands on the ground. So you'll see a kinematics problem like this on your homework tonight. It's just a specific case of finding particular solutions instead of general solutions for your antiderivative work. That's all for today, you guys, so you've got the rest of class time to work through this homework assignment. You've got a few more problems than normal for your homework, and that's just because you have several in the 5 through 39 that are just rote practice of practicing with power rule and with your trig function work.